Okay, part 2 of our titration. We are now adding 10 milliliters of sodium hydroxide to our reaction. So here's my burette with the sodium hydroxide, that's 0.30 molar. And now in my flask, I have 25 milliliters of weak acid. That is at 0.30 molar, and I'm going to add 10 milliliters of sodium hydroxide to this. So now we have to do a dilution. We have to change, because what we want is what's the pH inside this flask. So now instead of having 25 milliliters in this flask, we're going to have 35 milliliters in this flask. So what we need to do is we need to figure out what is the concentration of acid in this flask and what is the concentration of base in this flask. And we need to do that. First, we need to figure out how many moles of acid are in the flask, how many moles of sodium hydroxide are in the flask, what are the concentrations, what is the chemistry. So this is step 2. We are adding 10 milliliters of sodium hydroxide. So the first thing I want to do is I want to determine how many moles of weak acid are in the flask. Moles, not molarity, and I'll tell you why in a second. Next, what I'm going to do is I'm going to determine how many moles of base are in the flask. How many moles of sodium hydroxide are in the flask. Because then what's going to happen is the number of moles of acid and the number of moles of base are going to neutralize each other. Whatever one is left over is then going to affect the pH. But something else is going to happen, because remember, when an acid is neutral, when this base is neutralized, it's also going to produce the conjugate base. So let's work through this, and then I'll talk through the chemistry that's going to happen next. First, let's calculate how many moles of weak acid are in the flask. Okay, so I'm going to do this in liters because I have the molarity, which is moles per liter. So instead of saying 25 milliliters, I'm going to say 0.025 liters. I have 0.025 liters at a molarity of 0.30 moles in 1 liter. So liters will cancel, and I will have 0.0075 moles of HA in this flask. Okay? So now let's see how many moles of sodium hydroxide are in this flask. I've added 10 milliliters. So again, I'm going to say 0.010 liters, 10 milliliters. And again, it's the same concentration, 0.30 molar. So 0.30 moles and 1 liter. That means I have 0.0030 moles of sodium hydroxide. Okay, so that's what's in here. So now let's think about what chemistry is happening when you have a weak acid with a strong base. So when you have 0.0075 moles of HA, weak acid, plus 0.0030 moles of sodium hydroxide, that means that 0.0030 moles of HA is neutralized by, because this much sodium hydroxide is going to neutralize that much weak acid. It's neutralized by the strong base. Also, during the neutralization, the same amount that was neutralized, 0.0030 moles of conjugate base is going to be produced, conjugate to this weak acid. And 0.0045 moles of HA is remaining. So this is written out what is happening with the chemistry. So remember, when we have a neutralization reaction, acid plus base gives you water plus salt. So when I have acid plus base gives you water plus salt, this salt that is being produced during the neutralization is going to contain the conjugate to my weak acid. So when I have HA, I'm just going to use HA instead of HF. HA plus my base, sodium hydroxide, I produce water. That water came from here, this hydrogen and this hydroxide. But what is the salt that you're producing? The salt that you're producing is sodium, and in this case, fluoride. But I'm just going to say A because that represents this HA. Maybe it would be less confusing if I just called it hydrogen fluoride instead of HA. So let's just write this again. HF plus sodium hydroxide produces water plus sodium fluoride. So this is what's happening during the neutralization. Remember, this generic acid that we're talking about is really hydrogen fluoride. So now what do I have? I have a weak acid and I have a salt that contains its conjugate base. During the neutralization, you are also producing the conjugate base. So two things are happening. The sodium hydroxide that is being added to this flask is neutralizing 0.3003 moles of the HA, meaning you only have 0.0045 moles of the HA remaining. But in the neutralization, it also produced 0.0030 moles of its conjugate, F minus. All of the sodium hydroxide is used. So there's no more sodium hydroxide. We only have 0.003 moles of sodium hydroxide. It is all consumed in this neutralization. So now what I have here is a buffer system. Remember, a weak acid and its conjugate base. So now I can solve for the pH by using the concentration of weak acid and the concentration of its conjugate base in this flask. They're not these concentrations. These are the initial concentrations. So what we just said was now, in this moment, after these 10 milliliters have been added, what we have remaining is weak acid, hydrofluoric acid. I have 0.0045 moles of hydrofluoric acid remaining because I had 0.0075 and 0.003 moles of it was neutralized. So now I have 0.0045 moles of HA remaining. I'm going to solve for the concentration. If I have this many moles, what is my new volume? Well, I'm going to divide moles per liter. Well, what's my total volume in here? 10 milliliters plus 25 milliliters. It's going to be 35 milliliters divided by 0.035 liters. It's important that this volume contains the volume of base that you added. So 0.0045 moles of HA divided by a new volume of 0.035 liters equals 0.1287 molar. So now the same thing for A minus. 0.0030 moles of A minus, that's what was created in the neutralization, divided by the volume, which is the same, 0.035 liters, gives me a concentration of 0.0857 molar. So now I have a buffer. I have the concentrations of weak acid and conjugate base. Now you could solve this buffering system, solve for the pH one of two ways, either using the equilibrium table or by using the Henderson-Hasselbalch equation. I am going to use the Henderson-Hasselbalch equation. So I'm going to say pH equals pKa. Remember, the Ka was given to us as 6.6 times 10 to the negative 4. So to get the pKa, I'm going to say the negative log of 6.6 times 10 to the negative 4 is 3.18. So I'll say pKa equals 3.18. Okay, so Henderson-Hasselbalch equation says pH equals pKa. Maybe I'll just write the equation out first. pH equals pKa plus the log of base over acid. Okay, so that translates to pH equals 3.18 plus the log of the concentration of A minus, 0.0857 molar, divided by the concentration of H plus, my acid, 0.1287 molar. And now you just solve for pH using this equation, and you should get 3.00 as your pH. So pH equals 3.00 after 10 milliliters of base is added. So now let's put that on our titration curve. So this is step 2. I've added 10 milliliters. So here was step 1, I added 0 milliliters. Step 2, I've added 10 milliliters of sodium hydroxide, and the pH is 3.00. So at 10 milliliters, my pH is 3.00. So here was 0.1 with 0 milliliters, here's 0.2 with 10 milliliters at 3.